in the wrong place again. Right, hello everyone. I hope that my sound is coming through okay, because I've got a big fan about the size of a helicopter running just outside the door, and I've left the door open so I can get some fresh air in here. Otherwise it's going to get really, really hot under the stairs. It's a hot day. It's good to see so many of you tuning in. Hello. Sounds pretty crisp. That's good. That's the various software things I've got that are desperately trying to stop it sounding like a helicopter taking off. I want a nice, easy, gentle day today because we've just had a half term, which was not a holiday because as a teacher we've been busy deciding grades for people and marking things to decide grades for people in year 11 and year 13. So I want a nice, easy day today. So we'll see how this comes across. I've dug out some questions from the OCR about waves. They're A-level questions, but there's a lot in there that GCSE students can access. So I think that's not a bad thing. I think we're going to be okay with going through these waves questions. And if we finish it before the hour, then that's great. We can finish it before the hour. We'll see what happens. So let's get cracking. Let's switch this across. So these questions, rather than having what paper the question was from before each question, I just thought I'd put all these up front to satisfy the OCR instruction that if I'm going to use their questions, I have to declare that the questions are from OCR and copyrighted to OCR. Show where the questions came from. These are the papers whence the questions came. And then include the questions in their entirety. Well, I've done that because I've used their own software to spit out the questions. So this was a bit quicker than hunting through the papers individually. And what we'll do, I'll pop first of all the question down into the Discord chat, and then I'll let you vote for whether you think the answer is A, B, C, or D. So we're going to go with question 1 to start with. Don't vote until I say. And then we can always have a discussion about it. So, reactions. Where's the A? Don't make me hunt for it. A, there it is. Reactions. B. Where's the B? There it is. Right, I'm a bit slow because these aren't the latest ones there, so just wait for me. I'm like an old man trying to use technology right now. C. There it is. And lastly, D. Okay. The options are there. Vote for which one you think is correct. Yeah, I tried that, Pranav. What it did is it showed me every single emoji that happened to have an A in it. And then the same for B and C and D. So it was not as successful as I thought it would be. That was what I thought, Wombat. It'll be a bit quicker going forward. Okay, so it seems like it's unanimous on C. And it is. It is. I used a capital A and it was not Pranav, so I guess it works differently for me. Never mind. Yes, so yeah, the answer is C. It looks like exactly. It looks like everyone's got the answer. So a progressive wave for your GCSE students who aren't sure what this is going on about. Progressive wave just means the wave energy is being transmitted from one place to another, which is what you understand waves to be. A way of transmitting energy without transmitting matter. A displacement time graph, well, you've met the idea of displacement already in GCSE, possibly. You might not have met it, but then you might have met it in Key Stage 3. Displacement being a distance that you travel in a particular direction. And so this is looking at a particle, some particle, which is oscillating. It is being displaced in the positive direction, then displaced in the negative direction, then in the positive direction, and so on. So it's oscillating around some position. And if we plot a graph of that displacement versus time, we get something that looks like this. Fine. The question asks about being 180 degrees phase difference. Now, if you're a GCSE student, you've never met the idea of phase before. The phase is just a way of addressing where we are in a wave, a sort of a coordinate system. So if we say this is the start of the wave, we could describe this position in the middle. Hello, 𝗟𝘂𝗲𝗲, that is. Hello to you. Yes, we could describe this point in the middle here as being half a wavelength, if this was distance on the x-axis. Or we could describe this point here as one whole wavelength, and this one as a wavelength and a half. Hello, 𝗟𝘂𝗲𝗏. And that's one way of addressing the position in the wave. We've got time on the x-axis, so we could address our position in a wave. The word position here, I'm using quite flabby as a word. I mean sort of a coordinate and a way of addressing where we are in the wave. We could say this is half a time period, this is one whole time period, this is 1.5 time periods. This would be a quarter of a time period, this would be 3/4, and so on. But there's a more general way of addressing our position in a wave, which doesn't depend on whether it's time on the x-axis, okay, or whether it's distance on the x-axis. There's another way of doing that. And that would be to use an angle. So if we define this point here, this address of the wave as 0 degrees, then this would be one complete oscillation, and one complete circle we describe as 360 degrees. And so this point in the middle here would be half of one complete oscillation, half of one circle. That's 180 degrees, and so on. So you are comparing to point X. Point X is here. If you shift the origin, this 0 degrees to here, then you shift the 180 degree point to over here, which was, as you've all correctly said, C. So for GCSE students, I hope that was helpful a little bit, maybe, because you might use that later on. For I don't know why I rubbed that out. For A-level students, well, you probably already knew all that already. So let's have a look at question 2 then. It's worth 1 mark. You should, hopefully you can read all that. So I'm going to go ahead and prepare to receive your answer for question 2. There are some longer questions coming up. Don't vote yet. So there are some longer questions coming up. So don't fret and get all panicky that they're all very basic questions. That was a little bit faster. Now they're all there. Okay. When you're ready, you can go ahead and vote. One person's voted. Ahoy, AVAX1 USS. Good to see you. Okay, so it looks like 6 people have voted for A. Subtracting 1 from these numbers because these numbers below, because one of them is me. 7 people, 8 people have voted for A. Okay, it's unanimous, it's A. That's good. And again, this is actually a GCSE level question. It's come from an A-level paper. but GCSE pupils can definitely access this question. So as before, we've got a displacement time graph for some particle, an air particle that's oscillating. The equation we're going to use here is the one that relates the speed of a wave, the wavelength of a wave, to some other quantity. Well, that's going to be wave speed equals wave frequency multiplied by wavelength. We're asked to calculate the wavelength, so we rearrange this equation to get wavelength as the subject, like this. So far, so good. Wave speed we are given. We know what that is. Frequency we don't. But we do know that this wave, this trace on this screen shows 1, 2, 3 complete oscillations. So that is 3 time periods. And we know that frequency is the reciprocal of time period. So we can take this equation, make it wavelength equals c multiplied by t. Let's get my capitalization right, shall we? C multiplied by t, the time period. Because if you divide by frequency, and frequency is 1 divided by time period, you end up multiplying by the time period. And then we can just plug our numbers in. So C was 340 meters per second, multiplied by t, which is a third of 6 milliseconds. So that's 2 times 10 to the negative 3, because it's milliseconds. And that gives you the answer, which, you know, was pretty unanimous. Good. Okay, so question 3. I think there's a few more of these multiple choice ones. Question 3. I'll load up the question ready. When you're ready, go ahead. If you get any questions at any point, please do ask. Or is there anything you want me to go over again? Just ask. Trying to keep it nice and basic to start with before we get into some better questions. So when you're ready, you can go ahead and vote. Three people have voted. Other people are still trying to visualize it. Again, this is a GCSE question. Although it's on an A-level paper, being able to visualize waves is a sort of a GCSE level thing. So if you're a GCSE student, what I'm trying to say is don't be put off by it. Don't be spooked by it. Go ahead and try and answer it. I imagine you're all being swayed by the fact that 7 people have said the answer is B. Yeah, it is B. So very quickly explaining why. If the wave is moving from the left to the right, which we've just had the hump of a wave passing P, which means P is going down at the moment. From the peak of the wave, we call the crest, down towards the trough. The wave is moving from left to right, so P is dropping down. The next part of the wave that P will reach is the part that's here behind P. So it's going downwards. Cool. Okay. Question 4. So we've left multiple choice behind us. I think we've got some more multiple choice coming up towards the end. Yeah, one more multiple choice towards the end. But question 4. Hopefully you can see that okay. Let's just scroll across a little bit so you can see the whole question. It's worth 2 marks. And you've got, it's getting a little bit more complicated now. Remember that I said that waves were, the best way of thinking about them, I said this not last week, the week before last, the best way of thinking about waves is they are some sort of sinusoidal influence. What we've got here is 2 of these sinusoidal influences, which are occurring at the same time in the same place. some place called point X. And we were asked to state with a reason the motion of the particle at point X when both waves are present, 2 marks. So I can see a few of you typing your answers. That's great. If you're not typing your answer yet, listen, it doesn't matter if you get it wrong. Really doesn't matter. Give it a bash. Give it a try. If you've just tuned in, maybe this is the first time that you have seen this sort of thing, maybe the first time you've done this sort of thing, and you're not on Discord and you're wondering where are all these people sending these messages, there's a link in the video description to the Discord channel. So you can get yourself on Discord, just request the ability to send messages through Discord. It'll get the instructions are there how to do that. Then I'll switch you across, make you a participant, and then you can join in. Loads of people are typing at the moment. I can keep seeing the things flicking up at the bottom. Okay, we've got an answer to dig into. So, due to the superposition of the 2 waves, good use of the word superposition. We mentioned this last time. What's happening with superposition? The 2 influences are both affecting this particle. That's all it means. Adding those 2 effects together. Particle will travel with a positive displacement to equilibrium. Not sure I understand what that means. With a positive displacement to equilibrium, then a negative displacement to equilibrium. Oh, I see. Positive to equilibrium, negative to equilibrium. I think I follow what you're saying there. I'm just going to scroll a bit so I can keep reading this one here. So you're describing the motion of the particle. I don't disagree with your motion. I think it's great. Positive displacement, the positive displacement has a greater effect than the... Sure. You could talk about the time period also, actually. Yes, you could, and that's a good idea. You've missed some key things there, which I'll come into in a second. You got the motion right. So P superimposes Q. Sorry, Jonathan. That's not a word that we'll be using. When you superimpose one thing on another, you can't see the original thing. So, for example, if I were to take a picture of some famous fast food restaurant clown-based mascot and then superimpose my face over theirs, you would no longer be able to see the face of the clown-based mascot. Whereas if you were to superpose my face and their face, you'd be able to see them both. So superimpose is the wrong word there. Now, that does actually matter. In A-level physics, you lose marks for saying superimpose. It's wrong. Both those effects happen. It's not a case of effect P happens, so effect Q doesn't. No, they're both happening. So, however, amplitude of wave P is larger. This is true. And so you're giving it a reason here. You're giving an explanation. Amplitude of Q, you say. I don't think it is. I don't think it is. And I think if you count the squares, you'll convince yourself, Jonathan, that you've been a little bit sloppy. I think you should look really close. So, 𝗟𝘳, aren't the waves in antiphase? They are. That means we're going to get some destructive interference. And that's exactly what Wombat has just said here. You said there are nodes. Whoa there. This is a progressive wave. So there will not be nodes or antinodes. This is a progressive wave. Just because you can see the 2 waves sort of interlaced over the top of each other like this, this is this does not mean that it is a stationary wave. For a particular particle, it is oscillating. That is what we are looking at. So I suppose it could be a stationary wave. But it doesn't actually matter. Right, so let's keep reading this. Do a superpose. They oscillate in opposite directions, meaning the parts of the amplitude cancel out. Yeah. Can we put some numbers on this? 𝘬𝘂𝘀𝘶, you're right. Because they have different amplitudes, there will still be oscillation of X. And Wombat was correct before. Wombat said that the displacement is initially positive, then negative, then positive. Wombat described it as being a positive displacement back to the equilibrium, then negative displacement back to the equilibrium, then positive displacement back to the equilibrium. Great. You can do better, though. Now, you can't describe the time period because we have no numbers on the x-axis. The displacement, we've got no numbers on the y-axis, but it is drawn to scale. So this is where Wombat comes in now. At half a time period, amplitude is 0. No, Wombat. No. The displacement is 0. The amplitude is the maximum displacement, which for P is 5 small squares, as I count them. I think that's 5 small squares. And for Q is 2 small squares. So what will be, it happens, don't worry about it. So what will be the amplitude of the resultant phenomenon, of the superposed wave, probably the wrong word, the resultant wave? The amplitude of P is 3 times larger. I don't think it is. Looking at it, I think Q is 2 small squares amplitude and P is 5 small squares amplitude. That's what I see. Now let's add those two effects together. So at the points, this is do make sure that you're watching this in high resolution. So at the points that Wombat identified here, 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 and here, the displacement is 0. So 0 from P plus 0 from Q is 0. Boring. If we look at these points here, here, and here. So let's have a look at these. We have got 5 positive here, displacement, and 2 negative displacement there. So at this position that I'm marking with a green vertical line, what is the resultant displacement going to be? Three small squares. Great, but we don't know the value of a square. But I can write what the amplitude of the resultant will be in terms of the amplitude of Q or P. So I would be tempted to say that the amplitude is going to be 3/5 of the amplitude of P. And I probably wouldn't write it like this, but I'm just making some quick notes. It's still too, yeah, Wombat, you've said that it is less than. Yes, but we can quantify it. If the maximum displacement of the resultant wave is 3 small squares, then it is 3/5 of the maximum displacement of... But yeah, okay, we're not given numbers, but we can still be quantitative because we've still got a scale. It's drawn to scale. We can still count those squares, so we can still put some numbers to this. Now, is that going to be on the mark scheme? Possibly not. And again, I don't want to look at the mark schemes. That's not what I'm all about. Probably goes more detailed than it needs to be, but I would always prefer to go more detailed than less. If you're a GCSE student watching this, the principle of superposition of waves is perhaps a little bit beyond GCSE, but the idea that you can add two vectors together is not beyond GCSE. What we've got here is a vector up. I'm talking about the position where there's a green line. I'm just going to draw it over here to the right so there's a bit more space. That is 5 long. Then we've got something which is 2 long in exactly the opposite direction. We add those two vectors together and we end up with something that is, this is not to scale. What has happened there? We add those two together and we get something that is 3 long. So 5 long up, then 2 long down. We end up with a resultant that is 3 long. That is GCSE level. But applying vectors, displacement is a vector, applying the principles of vectors to waves, that's A level. That takes you that one step further. So I would give an answer just like wombats, but then I would go deeper and start talking about the relationship between these amplitudes, because you can. I would be extra careful not to confuse this with a stationary wave or a standing wave, saying things like nodes and antinodes. That's not correct. I mean, it might be a stationary wave. It might be. But this is against time. So we're looking at a single particle at point X. That thing is oscillating. That's what it's doing. It's just oscillating. But it's being influenced by these two different effects, P and Q, and the resultant is an amplitude of 3/5 of the amplitude of P. What I could also then go on to say, it's got the same frequency as P, it's in phase with P, because it is in phase with P, the resultant. I can give all this detail. I do not know what's going to be needed for 2 marks. But this is not a list principle question, which means that I can give more detail that's needed and not risk losing marks, as long as I don't say anything that contradicts something that's correct, that I may have already said. That's called talk out in examiner speak. Talk out is where a student talks himself out of a mark. The list principle, if you've never heard of it before, incidentally, is if it says list 3 things that are the same between 2 waves, or list 2 things. If you go on to list more than that, then you risk losing marks. It's not worth doing. Okay, question 5 then. Question 5 is worth lots of marks, 4 marks. Big money question. We talked about this exact effect last time, a fortnight ago. So let's see how you get on with this one. See, people are still typing. Draw a sketch. It's always a good idea to draw a sketch. It's a good starting point. Says several people are typing. I should put some background music on while this is going on, shouldn't I? Maybe not. Ooh, answers. It's probably going to be a character limit here. So, given both the speakers a frequency of that, it means the wavelength is that. Yeah, two significant figures, sure. For both of the speakers. Both the speakers are progressive waves, the speaker which overlap certain points where superposition takes place. Of course, it takes place everywhere. That's the point. Everywhere there's superposition happening. Everywhere. When the waves are in phase, constructive interference, music is loudest. I don't know if I call it music, but yes. Then it says when they are in antiphase, minima are formed and the music is quietest. Yeah. This concept carries through the 30 meters to the row of seats where it'd be louder for some, quieter for others. Yeah. I mean, you can go, Charles, you can go deeper than that, can't you? You've done one calculation. It does say you must include calculations, plural. And I can think of one other very sensible calculation you could do. The other thing I would say, just before I look at Wombat's answer, the other thing I would say, Charles, is your answer meanders quite a lot. It says describe and explain. So start by getting the thoughts right in your head, then just give a description. What do different people along this row here? That's what it asks for, along the row. And then give your explanation. And that doesn't need to be, you know, too meandering. You just say certain points. So don't apologize, Wombat. Do not apologize. The whole point of these sorts of sessions is for you to share your thoughts in a completely friendly way and get help. It's not about, oh, I'm not perfect. It doesn't matter. No one's perfect. I make mistakes. You've seen me make so many mistakes. So c equals f lambda. Wavelength, good. Therefore, that distance interval from a speaker will result in the loudest sound. Okay, I disagree with that. Superposition of waves traveling in different constructive interference. So far, the people in the crowd, sound will be the loudest, then quieter, then louder than again. So you've got the idea there that as we move along the row where people are sitting, it gets louder, quieter, louder, quieter, louder, quieter. Perfect. And that's something that I didn't think was in Charles's answer. So that's perfect. You have given a description. You haven't given, well, what might be nice is a distance between where it's loudest and then where it's loudest again. That would be a nice calculation to do. The quietest part is due to superposition of the waves where the destructive interference takes place. True, and the loudest part is where superposition takes place. Superposition takes place everywhere. But yeah, what I think Wombat's answer has that Charles's doesn't is a clear description of what you would experience if you were sat on that row and you shuffled your way along, or what different people along that row that's 30 meters from the 30 meters from the stage, what they experience. You could have been more quantitative with that. Your explanation, I think, is okay in the same way Charles is. You talk about constructive and destructive interference, but you've missed something that I think is critical to making sure we get full marks. Due to superposition of the waves, both speakers moves along the rows. They walk through regions of no sound. It won't be no sound, because as soon as you move away from being in the middle, you're closer to one speaker than the other. So because the sound is spreading out, it's going to be slightly louder from that speaker. So it won't be no sound. In fact, that might well be on the mark scheme as something that would cost you a mark, saying no sound. So be careful of that. And I'll draw a sketch in a minute to make all this make more sense. The minimum is formed due to cancellation. Cancellation is fine. You can use the word cancellation. These minima occur every half a wavelength. I think so. Loudest part is that, then that, then that. So you're all okay. I don't think so. Right, let's draw a sketch. Yeah, I've got myself almost blank piece of paper. Let's draw a sketch. What I'm going to draw, we'll come to that one back. What I'm going to draw is a speaker. Here's the speaker. Another speaker. There's another speaker. And a row of benches, or whatever it is. Is it a bench, a row? I don't know why. I assumed it was a bench because I'm a fool. A fool, I tell you. Okay. Now let's consider a person sat here. And what do we know? We know the sound from this source has travelled exactly the same distance. I think so, 𝗏𝘳, I can't remember. As this distance. Those two distances are exactly the same. Therefore, this is something I don't think anyone mentioned. Antonio, you've got it. You've got the distance between maxima and maxima, not maxima and minimum. Nearly had it. You got the number right, but you didn't get the interpretation of the number right. These two distances are the same, so we will get constructive interference. Great, fine. Now let's consider somebody sat next to them over here. And I'm going to just change the colour. Someone sat next to them over here. Well, the sound has had to travel further. Oops. The sound has had to travel further from the speaker on the left. And less far for the speaker on the right. It's had to travel further for the speaker on the left. Well, how much further? If we trace it back, if this distance here, this extra bit of distance that the sound has had to go, is half a wavelength, then this will be a bit quieter. This person here is closer to this speaker here, so the sound from this speaker won't spread as far, so it will be a higher intensity of sound from this speaker than from this speaker, so we won't get complete cancellation, which is what Pranav suggested, but it will certainly be quieter. There'll be destructive interference. The reason why there's destructive interference is because there is a phase difference between the for the waves that have travelled from those two speakers, a phase difference of 180 degrees. So we get destructive interference. There's a path difference of a half a wavelength. Therefore, there's a phase difference of 180 degrees. That's what's happening there. Then we move a bit further over. We scoot ourselves over a little bit further. Again, I'm just going to delete some of this stuff. So if we scoot ourselves over a bit further to this place here. And at this place here, well, this sound has had to travel much further now. Perhaps in this place here, the path difference is now one whole wavelength. But if the path difference is an integer multiple of a wavelength, then the phase difference is an integer multiple of 360 degrees. So we would say the phase difference is 360 degrees, which is the same effect as 0 degrees. There's no phase difference. They are in phase. So we get constructive interference. Yep. Yep, absolutely right, Pranav. Absolutely right. So if you recall, if you're an A-level student, then you've got an equation that I'm going to quickly derive in my head. Give me a second. There we go. You've got an equation. Yeah, I think that's right. You've got an equation. Oh, I'm not sure now. Give me 1 second. Yeah, that's right. Yeah, that's right. An equation here, which you will probably have derived in your A-levels, which is W, the fringe separation. So that's between one point of high intensity and the next point of high intensity. That's what W is. D is the distance between the screen and I need another color. Well, let's go with this horrible cyan color. There we go. That is what D is. Distance between the middle of the two slits, or in this case speakers, and the screen, or in this case the row where the people are sitting. Lambda is the wavelength, and S is the distance between these two speakers, or you probably learnt it as slits for light. But do you know what? Whether it's light or whether it's sound, it is all waves. Waves diffract, waves interfere. That's the principle of what waves do. And so we can use this equation, which Antonio did correctly, and correctly calculated that the distance, that is a thick black, was it not black? Purple, thick purple pen. Let's get a thinner one. There we go. Antonio got 1.65 meters, which is correct. However, he interpreted that as the distance between one place where it's loudest and the place where it's quietest. That's not quite right. One loudest and the next loudest. And so if you halve that, you could say that every 44 centimeters, that doesn't seem right to me, 1.65 divided by 2, I can do maths me, every 82.5 centimetres, that sounds better, every 82.5 centimetres, should have been able to do that in my head, how embarrassing. Every 82.5 centimetres, the sound goes from being loud to quiet, then from quiet to loud, then from loud to quiet, and so on. That's the explanation. Superposition, yes, but we... Yeah, sure. Superposition. I think I was an order of magnitude out with what I said, actually. No, it doesn't matter. Right, superposition, path difference, phase difference, constructive and destructive interference. Relate it to diffraction from two slits. Use the equation, calculate those distances. You've got to do all of that if you want to get those 4 marks. 4 marks at A-level is hard to get. You need to put all of that in. Any questions about question 5? You can type your questions while I'm scrolling down to question 6. Hopefully you all found question 5 somehow enriching and useful. If you are, let's say, particularly interested in quantum physics, I know at least one person out there is a year 7 who's very interested in quantum physics, then these principles of superposition happen all over quantum physics. Yeah, sure, Wombat. I just hope I've got the calculation right now. Otherwise, this will be really embarrassing. So I'll do the calculation here. So we've got, I need to derive it again, stand by. Lambda over S equals W over D. Yep. So we've got this equation here. Yes, it is. You don't even know how cool. Okay, so I want to find out the fringe spacing. So that's going to be lambda D over S. Do I know lambda? No, I don't. But what I do know is the frequency and the speed. I know that lambda, oh, by the way, never, 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 never leave equal signs hanging. Never do that. So I know lambda is equal to C over F. So now I can write down W equals CD over FS. Plug my numbers in. 330 multiplied by, how far away are we? 30 divided by, what's the frequency? 1,200. I missed an opportunity to say, what's the frequency, Kenneth? Oh, I'm so embarrassed. I had such a chance and I blew it. Yeah, that sounds really fun, Pranav. Sounds absolutely great. Yeah. I've signed up to do a 5-hour course about quantum physics. No, not 5 slits, 5 meters between them. 5 meters between them. Pranav, yes, it's a song. Yeah, 5-hour introduction for quantum physics for 3 individuals who have no knowledge of physics really at all. I'm not sure how mathematically capable they are either. So it's going to be fun. It's going to be interesting. I'm looking forward to it. Okay, are we all good to move on? Well, we'll be okay. I don't want to cheat and just not have any maths in it, because you can't do physics without maths. So I want to do it properly. I'm trying to decide the best route through it. But it's by the way, that's an individual, 3 individuals who clubbed together to do those hour-long tuition sessions that I was offering for charity. They've decided they want to take me up on the offer. Rather than doing GCSE or A-level revision, they just want to learn about quantum physics. Great. Love it. Let's do it. So those sessions are no longer on offer. They've been sold. Okay, so everyone's reading the question. I'm doing the calculation myself, by the way. Oh, nice. I got a good number from it as well. Yeah, if you just type the number that you think you get, speed of sound in air. It's a very sensible philosophical question to ask, 𝗟𝘳𝘀. Yeah, very good question. Is dark matter real? Is anything real? Am I real? Or am I a construct of your mind? Yeah, type the answer, what you think the answer is to this. The A-level students right now are frantically drawing sketches to try to make sense of the question. Yeah, 𝗟𝘳𝘀, you've got it. Well done. Very, very impressive. Okay, so Pranav didn't get it right. Yeah, go for it, 𝗟𝘂𝘀. Go for it. So I really don't want to show anyone up, but I'm going to anyway, because it's good fun. Not to put people down, but to raise people up. Let's just, you know, some people are going to be upset by this or embarrassed by this, but 𝗟𝘂𝘀, as he's already said earlier on, is in year 7, and he's managed to get the correct answer. Whereas I know there are A-level physics students who haven't managed it yet. So 𝗟𝘂𝘀, you deserve a big congratulations for not just following this, but jumping straight to it and getting the right answer straight away. Let's see if your working reveals that you understand what's going on. Regular participants, by the way, on Discord, you are able to send pictures. So if you just want to take a photo if you're working rather than typing it all out, you can do that. No word from Charles for a while, or... Perfect. As easy as that. Oh, Pranav, yeah. Don't do that. Working on paint with a mouse. Yeah, perfect. Absolutely brilliant. Yeah, so I haven't heard from Charles for a while, Wombat, or James, or there's a few other people that appeared and then they haven't said anything for a while. I see Antonio's typing. Yeah, so you've basically got it. Okay, here is Antonio. Let's draw a sketch. We've got a particular wavelength, right? If we get loud sound, that means we have a stationary wave set up. So that means that the wave, this end is open, so the air can vibrate freely at this end, but it can't vibrate freely at the bottom. That is a fixed boundary. So this is a node, and this is an antinode. Our wave would be drawn, let's draw this a little bit clearer. This is a node, this is an antinode. So our wave could be drawn like this, reflecting off the bottom and then coming back. We've got exactly the same wavelength here. On the left-hand side, we haven't changed the wavelength or anything. We've got a node here. We've got an antinode up here as well. But because it's the same wavelength, we know this is a quarter of a wavelength, L2. Or it might not be a quarter, but that's the simplest case, the quarter of a wavelength. So that means it's going to come up like this, then back down to here. Let's try drawing this a bit better. It's going to go up like this. I don't think this is drawn to scale. And then up like this. And then it's going to reflect. Oops, I drew it like that, like this. Okay. So we've got a node there as well. And we've got an antinode. So it goes node, antinode, node, antinode, node, antinode. Okay. And what's the difference between those two? If you can see we've got the distance here of 1/4 of a wavelength, just like we had here, 1/4 of a wavelength, and this one here is 1/4 of a wavelength. Then what's left is half a wavelength. Now for stationary waves, as a general principle, distance between two adjacent nodes is half a wavelength. Distance between two adjacent antinodes is half a wavelength. If you draw a sketch, you can see how that makes sense. The wave here is 3/4 of a wavelength that fits into the tube because it's bound at the bottom but open at the top. Yeah. So you get nodes every half a wavelength, antinodes every half a wavelength, regardless of it being bound at the top and bottom, or open at the top and bottom, or bound at the top and open at the bottom, or vice versa. You'll always get the same thing. Distance between two adjacent nodes or two adjacent antinodes is half a wavelength. And so as we make the tube shorter, basically by pushing it into the water, we go from this being resonance, nice and loud, resonance. Well, then we lose resonance. We're not able to set up stationary waves anymore. The length of the tube is wrong. And then we get resonance again. So the difference between these two is equal to 1/2 of a wavelength. And then you can see the working that, I think it was Pranav, used paint with his mouse, which was very impressive for paint with a mouse, I have to say. It's very impressive paint with a mouse work. Although it goes off the edge of the screen. But you can see it on Discord. So 50.6 centimeters minus 17 centimeters. Double it to get the wavelength, then multiply it by the frequency, and that gives you the speed, which you get 336 meters per second. So show your reasoning. That just means you've got to have your working there. We've got a few more, but they're getting quite repetitive now, I think. So it repeats the experiment, but the frequency of the sound is 5,000 hertz. State and explain whether these results are likely to give more or less accurate value. Oh, actually, I like this question. Yeah, Pranav, you know you can get a graphics tablet like the one I used to write with. You can get that for about 30 quid on eBay. They're not too bad. And then you can use a pen. It's much easier. Yeah. Now I've got a spare one you could borrow, but it's out of batteries, and a colleague of mine, lost the charger, so I can't actually charge it up. Anyway, so what do you think for B? We've got about a minute left, so let me know what you think for B. Wombat's right. Right, but it's going to be a more accurate frequency measurement. I mean, but 𝗟𝘂𝗲𝗲, yeah, I mean, it's a really, really good answer. A really, really good answer. Smaller lambda, smaller L, going to be less accurate. It's not just a little bit smaller. It's a tenth. A tenth of the frequency. Sorry, 10 times the frequency means we're going to have a tenth of the wavelength. A tenth of the wavelength means that this goes down to 0. We're talking differences on the second and third significant figure, which are important now. I wonder if that's going to make much of a difference. Right, now I'm out of time. I'm not sure where I sit with this. The way I would approach this is I would write the expression for the speed of the wave algebraically And then I would consider what happens to some of these numbers if the frequency went up by a factor of 10. If the frequency went up by a factor of 10 and I can measure to the nearest hertz, then I've got 10 times more accurate frequency, or 10th as much uncertainty of my frequency. But then what does that mean for the uncertainty in my length? Now, because I am subtracting two lengths, then I am going to essentially double the absolute uncertainty in the length. So I think that the reduction in accuracy of length is going to become more significant than the improvement in accuracy by having a higher frequency. So I think 𝗟𝘂𝗧𝗏 is correct. But at A level, for 2 marks of this amount of space, you would have to go into that sort of detail, I think. Right, we're out of time. So next time it is optics. We are starting with optics, and again we're going to do a GCSE optics session to start off with next week. So do tune in. I don't think this is anyone's first time, but just in case it is, I'm going to put this silly thing scrolling across the... It's not working. This silly thing scrolling across the bottom, just to say, please, can you subscribe? Because I'm currently at 556, 557 subscribers, something like that. Fantastic. Again, my target is 1,000 so that I can get this embedded in my website. So help me out if you like. Share it around. Keep in touch. Keep putting those questions on Discord. Lovely to see the conversations that are going on Discord. Honestly, if you're not on Discord and you're just watching this on YouTube, you're missing half of what Physics with Keith is all about. The discussions on Discord are great fun. And stay safe. Have fun. I'll see you next week.